Do you ever wonder how come atmospheric currents or ocean currents are formed? Let's see if we can spend some time today to better understand it. You could see here on the map, this is one of my favorite map and it shows how we have trade winds in on our planet. As you could see here, we have Africa, and from Africa we have those wind going from east towards west. In the Pacific, we have the same thing from east towards west. And the big question is how come this is happening? And that's what we're going to talk about today. So let's see if we can have a better look at the map here and a bit bigger. Very good. So if you look at the map here, you will notice that we have an overall trend of what we have here. So here we have our planet. This is from 2008, 2010. Someone took all the data we had for the atmosphere. And here we have dust and cloud in our atmosphere. And you will notice here the trend going from east towards west on the Atlantic, from here east towards the west on the Pacific. And if you go on the other side here, you can see the trend going from the eastern part of Pacific going towards South Asia. You also have those wind going on above the the Indian Ocean. There we go. And it's interesting to see how there's a pattern that goes from right to left. You might wonder, why is this happening? So let's see if I can give you an example. So here we have a globe that represents our planet. And here I'll give an example of how things go. So right now it is about noon in Canada. So in Ontario, so we are right here at noon. That means that if you go into France here, it's the end of the afternoon. If we go on the western part of the US or maybe Hawaii, then it is the beginning of the day. And the reason for that is that we have our planet that is doing a rotation on itself. Now, when it's doing a rotation, what's happening? We have a solid planet with water on it that is turning, but we also have a layer of atmosphere on top of it. But as the Earth is turning, what will happen is that it's turning, but there's free, and the atmosphere is on top. And as the Earth is turning, and we have, let's say that I am here. So let's say that the Earth is turning, but the atmosphere is a gas on top of it. So the Earth is turning, and the atmosphere ends up dragging a little bit behind because the Earth is moving faster. So if we go back to our map here a moment ago, so let's see, we are right here. So here we have, for example, the atmosphere that is here, and we have a planet that is moving from west towards east faster than the atmosphere. And the consequence of that is that we have an atmosphere that, if you are on Earth, that has a tendency to go from east to west. Now, we've talked about in the last few months about the El Nino happening in Canada and North America. And the reason here is that those trade winds, like along the equator here, they're not as strong. So that means here we have warmer ocean water at the top, and it's creating here wind that tends to be a bit warmer, and it's affecting our seasons, that is winter here. So the big question is, let's have a look at other patterns we can see here. So we see the overall big trade winds along the equator. But we also notice that we have, if you go here, so in Ontario, we are right here. If you see, we have a wind that's called a jet stream that goes from west to east going this way. And so you could see the wind going this way. And if you go south of the equator, we also see that there is a trend of the wind going from west to east at the bottom here. So here, there's a few things going on at this time. So let's see if we can look at our planet. If our planet had the sun, so let's see we have the sun here. And if our planet was a cylinder, what happened is that we have the energy of the sun that will be more or less the same for the whole cylinder. So here you have air being warmed up, going up. We also would have air cooling down as it went into the atmosphere and going towards the ground here. So we would have cells that are like this on our planet. The difficulty, though, is that our planet is not a cylinder. Our planet is a sphere. So if instead of a cylinder, I have a sphere like this, so that means that, oops, the energy from the sun is not the same here and here compared to the equator. And furthermore, we have here a circumference at the equator that is much smaller than the circumference here further north in latitude. So what happens is that we have wind that wants to go up, but it's squeezed here. So what happens is that we have a tendency to have wind going north and towards the east. And that's what brings this idea here. And let me show you the map again. That's what brings this idea, a tendency for the wind to go from west to east here along the border of Canada and the States and Europe, and the same thing further south. And you see there are some consequences of that for ocean current. Now here we have, you could see a trend going from west to east here. So we have what we call the jet stream. The jet stream is wind going from west to east here, and it's used by people traveling to Europe, for example. If you go from Toronto and you want to go to Paris, it might take maybe 6.5 hours, a little bit more, to fly from here all the way to Paris. However, if you want to go from Europe back to Canada, instead of 6.5 hours, it might take up to 8, sometimes a bit more, because the plane will go against the wind back to North America. So here we have what we call the jet stream. So let's learn about this one a little bit more. And by the way, all the links of the website I'm using will be in the description below. So a few things. So here I had my drawing. So we have the circumference of the planet here that is turning as a specific speed. Now, further north here, what happened is that we have wind or the atmosphere that is interacting here at, so we have miles per hour, so it's about 1600 kilometers an hour. But here the atmosphere is going at a specific speed going north here. But here we could see the speed is quite different. So what happened is that we have the wind is picking up. So the jet stream is made from the difference in the speed from this part compared to this one. So let's see if I have another example here. See if that can help. It doesn't help. I went to the website and I didn't think so. So let's go south a little bit. So here I have an example where along the equator, we have more energy from the sun. So the air warming up goes up. And then as it goes towards the space, it is cooling down. Now, the atmosphere cannot go up forever. So it needs to follow the gravity. So it goes up here and down here. But as the air cools down, it will end up going, being heavier, denser, and then towards Earth again. So there's big convection cells here. The polar cell here, how come it exists? It's because it's cold, the air goes down. And as the cold air goes towards the equator, it warms up and eventually it goes up here. Because keep in mind that the air going from the pole will not be able to go down all the way to the equator before it goes up. The thickness of the atmosphere compared to the size of our planet is very, very thin. And that creates what we call a jet stream here. And here further north, we have a polar jet stream. So if you notice in the last, so this winter actually in North America, we've had situation where in the prairies in Canada, we had minus like 45, close to minus 50 degrees Celsius. And the reason here is that we had polar air that was moving down here closer to this part. Next week, they're forecasting here in Toronto about 9 degrees Celsius. The only way it can happen is that we have warmer air that is moving up, and all of this is playing. Because here we have an example. Can I make this a bit bigger? We cannot make this one. Let's see if I can increase this in size a little bit. So here you could see we have the equator here, and here we have this jet stream that goes up and down depending how things are going. So by changing, what happened is that you end up with a situation where we have cold air that is either coming further south where it is affecting us, or sometimes we have warmer air that is going up towards the north, and therefore we have zigzags in these streams. Don't forget that air is a fluid and it's not very dense, and therefore we have winds going all over the place. And this is, so if you look here, so you could see this is the equator here, and we have the wind, a stream to the north here and a stream to the south. Now, if you've been going to camp, for example, you may have noticed that when there's no wind, the top of the lake is it's like a mirror. However, as soon as the wind picks up, then it's an uneven surface. And the reason for that is that when the wind picks up, there's friction between the wind and the atmosphere and the water. And the water is being dragged in one part or another. So for example, we have El Nino right now in this winter. So if we look at the map here, we have trade winds that are not as strong this year. That means that the water that is warm on the surface is not being pushed very far. And therefore, we ended up having warm water here that affects and brings some more water and warmer air in North America at this time. But as it brings some air here, we also have interaction with the polar air coming down. So that's why it's an uneven. Sometimes it's warmer, sometimes it's much colder, and it's tricky. When we have, for example, the opposite of El Nino, it's La Nina. We have trade winds, which are the winds here from east to west, much stronger. So it's pushing towards west, the top of the ocean water that is warm, and it opens up here some cooler water from the bottom of the ocean up to the surface. And therefore we have cooler surface water, which affects the North American continent. So let's see. So we have winds that are causing water, the surface water, to move. So if you take here between Africa and South America, we have those trade winds. So that means that we have warm water from the surface going towards, being pushed towards the west. However, we have here the South America, Central America, and North America preventing the water to go west. So what happened is that the water will go here in the Gulf here, south of the United States, and will have to go further north here. So let's see if I can see the motion. So we have, for example, so let's see, I have a nice videos here. Very good. So as the wind is going towards the west, it's pushing some of the water further north. Now here we have North America, and we can see here the current, that is the surface current that is moving towards north here. Now that creates something interesting, because we have the wind going from Africa towards the Americas, and it's pushing the warm water that is at the surface towards the west, cannot cross here North America, and therefore change direction and goes further north here. This is what we call the Gulf Stream. The Gulf Stream is a stream of water from here, the equator area, going towards north. As the surface water goes north, it cools down, therefore gets denser, and will go in further down in depth. So all the water going up this way will cool down, and then the volume of water will go at a deeper depth towards the south. So that's how we can have water going north and then coming south. And that's creating some things for our society. Because if you think, we have here our jet stream pushing air from west to east, going over the Gulf Stream. And what happened is that we have warm air that gets to Europe here. So often when you think of Europe, you think of England. We think of in Paris, for example, in Europe, in Spain, in Portugal, close to the ocean. We rarely talk about snow, and the reason for that is the air is warm enough that the water will go and will not crystallize. We have rain, but rarely snow. It does happen that we have snow there. It lasts for a few days. Often they stop. Everything stops because they don't know how to deal, or they don't have the resources to deal with the snow. They wait a few days and then the snow melts and they continue. And the reason why we have warmer Europe is this idea that we have the wind going from west to east going over this warm water. If you like history and you go back in the years 1400, 1500, 1600, and there was a time when it was the Dark Ages, we suspect that during that time, the surface current temperature was a bit lower, which brought lower temperature in Europe, which created issues with farming, with production of food, and all the issues that happened in that time. Now, the water warmed up, and then Europe went out of the Dark Ages, and that will be what happened. If you like history. Now here, we notice that we have cold air going this way. Now, I talked about the fact that we have the trade winds pushing here on the Atlantic, the warm water. But in the Pacific, we also have the trade winds going from east towards west and picking up here the wind and following along the equator, going here south of the Indian Ocean, and then going south of Africa, and then again back to Central America. Now, interestingly enough, earlier we did mention that we have, so if I go here, we have this wind in the southern part of the Earth here. We have the southern hemisphere, wind from west going east. And if you see here on this graph, we have the surface current that is going here from west to east. And the reason, the engine pushing that are the winds in the atmosphere. So over the millions of years, there's been an equilibrium. And then we have this cycle here of water going north, cooling down, and then so we have a large cycle, which is amazing. So here they often call it the conveyor belt. So we can have animals following these currents, we have nutrients, we have ships using them to be able to move. So this is something that we learn and we use a lot. How are the surface currents? Let's see. How does the current get their energy? There you go. It's from the trade winds and the winds of the atmosphere. Now, as I was doing my research, I was looking at another thing that was interesting. It's about tide. And let me show you this video that I saw that was amazing. So we start early. So this is from the NASA Scientific Visualization Studio. So we have here a two-dimensional map of how tides are working. So in a moment, they'll take the map and they will tilt it on the side, and then we're going to see what is happening. So here we're in North America. So if I stop here, we have the high tide. Let's see. We have the high tide here on the eastern part of Canada. And then during that time, we have low tide here in Europe. We have high tide here in Alaska and on the western part of the Pacific. If I continue a little bit, then there are changes that happen. Now in the North American part here, I have low tide, but I have high tide here. And here, this tide here that was high by the South Asian portion of Asia and Southern Asia is moving down. And then we have lower tides happening right here. And if we let it go a little bit, you could see that there's a switch, and it almost looks like it's turning counterclockwise here and counterclockwise here. And the big question is, how come we have those tides? Now, we talked about the fact that we have the atmosphere that is moving. We also have ocean current, but there's also something else affecting our ocean. Now, this is a map, so the height here are exaggerated, but it tells us much about what is happening. So let's see if we can figure out how come we have those tides. So let's see. So we're going to do our planet. So Earth is here. And we have the moon. Let's put the moon here. So what happens? So we have the moon that is attracted by gravity towards Earth, but we also have the moon attracting the Earth. So here there's a synergy between the two. So with two solid bodies, that's easy. However, because the moon is attracting the Earth and that we have water that is a fluid here, we have the second bulge that is happening right here towards the moon here. If it happens that the moon is rotating, so here if I have the sun, then eventually that moon is orbiting and the moon is right here. The consequence here is we have tides that are even bigger. And the tide, well, it doesn't reach the moon, but this is drawing. So let's see, we have the moon here. So we have the high tides. And thank you for your patience. The drawer had to work because we have an outing in a few minutes. Now here what's happening, we have the tides. However, the Earth is rotating. So if you imagine, so let's go back to where I am right now, which is North America. Let's assume that you are the moon and you're attracting the Earth. If North America is towards you, that's easy. Nothing changes because we are solid. But if you turn a little bit, what happens is that the moon is attracting the water of the Pacific Ocean. By attracting the water here, it creates low tide somewhere else on the Pacific Ocean. And as the Earth is moving, you are attracting, assuming that you're the moon, you are attracting the water, and therefore the bulge of water towards you is moving as we have the Earth that is moving. However, that bulge here is being stopped by here Asia. So what will happen is as soon as the moon is there, we have the Earth that continues, we have gravity here, but no longer there. So the water that was up here a moment ago is now not being attracted, and it will create a low tide. A bit like if you're taking a tub, if you are in a pool or you're in a bathtub, and you are going from one side to the other, you have big waves. If you go on one side, you have a big wave on one side and low waves on one side. And then if you stop, then the water will just go back and take its place. Same thing if you're moving from one side to the other. It's the same thing. So what happened here, the moon, if you're the moon, is where Asia is, nothing much is happening. Nothing much is happening. But then if we have, as soon as we get here, we have the moon attracting the water, and then we have this big bulge of water that is going towards North America and then stops at the edge here. So what happens is that we have this idea of a bulge that is towards the moon, depending where the moon is, and the bulge is still towards the moon, but the Earth changes the way the tide goes up and down. So I saw this video yesterday, and I thought I had to show that to you because I had never seen this, and it's kind of amazing to see how it goes. One of the main reasons we can see this kind of data is that we have more satellites in space. We have more information coming all the time to study our Earth. So this is another one that is a global circulation of water based on tides. It's beautiful. It's always interesting. And if we want to add some culture, because it's always fun, this is Mount Saint Michel in France. It is an island, and on this island there's a monastery and a castle. And here we have the high tide of 2015. When there's a high tide, we have this island that is isolated from the mainland. However, in low tide, then you can see the water is going away, and then you can access this island through the road. So this is a great destination for traveling. And I thought that's a nice example of how we have waves that is affecting how people need to deal with society. Can I make this a little bit bigger? Very nice. And I have here the link of these pictures in the comments below. When I go to Quebec City to see my family, something interesting, even the St. Lawrence River, we can have tides that goes, so the water level goes up and down, maybe 1.5 to 2 meters, depending on the time of the year, twice a day. So it's interesting because if you go, sometimes you have to climb the ramp up the boat to cross the river. And then when you come back, sometimes then you have to go down the path towards the boat, because with a couple meter difference depending on the time of the day, it's always interesting. And that's why in Quebec City, we don't have a bridge that crosses anymore, like an ice bridge that crosses from south to north shore, because there's too much of a tide and it's too hard to create the bridge, especially that we have boats going up and down. It would be a lot harder, and with warmer temperature, I don't think it would be possible to do that anymore. On this is the topic I had for you today, on how we can have a global circulation. So circulation of air, that is a fluid, of water, that is also a fluid, at a planetary scale. I thought you'd like to hear that, and I hope you're going to have a great day. On this, I'll see you next week, and be great. If you have any questions, don't hesitate to write them in the comments below. I'm here to answer your question as we go along. And in the meantime, I'm going to put here a link to another video that you will enjoy.